Let's now consider batteries connected in series and in parallel. We start with n cells connected in series, such that they assist each other. This means that all cells are connected with same polarity as shown. The net EMF is hence equivalent to the sum of the individual EMFs. So we have total EMF E, which is equal to E1 plus E2, and so on. And so is the total internal resistance. So if R1 is the internal resistance of battery 1, R2 of battery 2, and so on, then we have the total internal resistance R, which is R1 plus R2 plus up to the end battery. Now, if a cell, say E2, is connected in reverse polarity, so imagine that we reverse the connection of battery 2. Compared to the others, we have the negative terminal of battery 1 connected to the negative terminal of battery 2. So like that, we say that battery 2 is connected with reverse polarity. Then in this case, the net EMF is found by subtracting E2. However, you must note that the total internal resistance remains the same. And this is because, with regards to resistance, polarity direction is irrelevant. So the total resistance is still R1 plus R2 plus up to Rn. Let us now consider n cells in parallel which are identical. By identical, we mean that they have the same EMF, all E, and the same internal resistance, small r. Then in this case, the total EMF is E, since these are all in parallel. And the internal resistance is found by applying the result for parallel resistors. So we have 1 on RT, if RT denotes the total internal resistance, then 1 on RT is 1 on R, plus 1 on R plus, and we keep on adding these till the end one, so we end up with N on R. So the total internal resistance RT is simply R on N. Now you must know that this is for identical cells in parallel. If we had to have different cells connected in parallel, so different EMFs and different internal resistances, then the calculations aren't as straightforward as I'm showing here, but will involve using the so-called Kirchhoffs laws, which shall be discussed later on. Now, let us consider two batteries connected in opposite sense to each other. In the diagram shown, the current, capital I, is being driven by battery S through battery T, so in this direction. And if you look carefully at how battery T is connected, then the current is driven in opposition to its EMF. Hence the title, current in opposition to EMF. So this shows that if VAB denotes the terminal PD across both batteries, so this is the terminal PD either across battery S, and it is the same as across battery T. However, since the current is flowing in this direction, then VAB must be greater than E the EMF of battery T. So that is why we are stating this, that VAB is greater than E, and hence, to find the current flow, it is the net EMF and the resultant EMF is VAB minus E, is the difference between these two, divided by the total resistance, which is small r. The total resistance is the internal resistance of battery T. So we get this equation, the current is VAB minus E, the net EMF, divided by the internal resistance R. And if we arrange, we get VAB is equal to E plus IR. Now, in other words, if we look carefully at the result we've got here, we are saying that the terminal PD of battery T is equal to its EMF plus, this time we've got a plus, the lost PD across T. So this contrasts with what we said earlier on, where the terminal PD was equal to the EMF less, so minus the lost volts, in the case where we had a battery that maintains a current in the same direction as the EMF. Kirchhoff's laws are applied when a complicated system of electrical conductors, which is called a network, is to be analyzed. These consist of two laws that are an extension of Ohm's law to networks, and both are based on the principle of conservation. The first law refers to any junction in a circuit and states that the total current flowing into a junction is equal to the total current flowing out of it. In other words, mathematically, we are saying that the algebraic sum of currents at a junction of a circuit is zero. The normal sign convention is to take the current as positive when it is flowing into the junction and negative if flowing out of the junction. And here I'm showing a couple of situations. In the first, we have a current I1, which is approaching a junction, and the current leaving is I2 through here and I3. So we get a positive I1, a negative I2, and a negative I3. So sigma I equals 0. So the summation of currents is 0, gives us I1 minus I2 minus I3 is 0, or simply I1 is equal to I2 plus I3. So the current entering the junction is equal to the total current leaving the junction. If, on the other hand, we have this situation where we have I1 and I2 that are entering the junction and I3 that is exiting, then I1 and I2 are positive, whereas I3 is negative. So in other words, I1 plus I2 minus I3 must be 0, or I1 plus I2, that is the total current entering the junction, must be equal to I3, which is the current exiting the junction. Kirchhoff's first law is a statement of the conservation of charge. It follows from the fact that electric charges do not accumulate at a junction. In other words, the total charge entering a junction must be equal to the total charge leaving it. Now, Kirchhoff's second law states that round any closed loop in a circuit, the algebraic sum of EMFs is equal to the algebraic sum of all PDs in that loop. So mathematically, we're saying that the summation of EMFs is equal to the summation of PDs, which is the summation of IRs, since PD, V is equal to IR. Kirchhoff's second law is in fact a statement of the law of conservation of energy. Since basically here, all we're saying is that the net work done by the batteries must be equal to the net energy consumed by the components around that closed loop. To apply Kirchhoff's second law, the best way is to follow a few guidelines. So first, we have to decide about a way how to go around the loop. So this may either be clockwise or anti-clockwise, it doesn't really matter. The custom is to keep the same direction as the net EMF. Now, the EMFs will be positive if we pass from the positive terminal of the supply around the rest of the loop to the negative. On the other hand, EMFs will be negative if they occur the other way around. With regards to PDs, these will be positive if the current direction through that component matches the way we're going around the loop. Obviously, PDs will be negative if the current direction is opposite to the flow around the loop. Let's try to apply these guidelines in this situation. So imagine we have this loop, which is part of a more complex circuit. Considering the first law at junction X, if we label the current through E1 as I1 and that through E2 as I2, then the total current entering the junction must obviously be I1 plus I2. So that is how we are applying Kirchhoff's first law at junction X. Same if we had to apply it here. Now let's apply the second law. Sigma E is equal to sigma IR. So sum of EMFs is equal to sum of PDs around this closed loop. So, as we said, first we must decide about a way how best to go around the loop. Since we're given that E1 is greater than E2, then the best way to go around is in an anti-clockwise sense. So, as shown by the green arrow, from the positive terminal of E1 towards its negative terminal. If you choose to go the other way around, it doesn't matter. We would still get the same results. But let's stick to one way of doing this. So we have thus a positive E1 but a negative E2. If you look carefully at E2, its polarity is in opposite sense to that of E1. So sigma E becomes the net EMF E1 minus E2. All right. Another way of looking at this is that to go around the loop as shown by the green arrow, with regards to battery 2, it's as if you're leaving from the negative terminal of the battery towards its positive. So that shows that E2 is in a negative sense compared to E1, obviously. Now, with regard to PDs, sum of IRs. So we have I1 R1 across R1. Okay, so it's the product of the current through it times the resistance. And similarly, we have I2 R2 across R2. How are we going to decide whether these are positive or negative? By looking at the current direction through each component, we can see, for instance, that I2 is in the same direction as the way we've decided to flow around the loop. In other words, it matches the green arrow. Hence, I2R2 is positive PD. On the other hand, I1, which is in this direction, it happens to be in opposite direction to the green arrow. So I1R1 is negative. So sigma IR is simply I2R2 minus I1R1. So by Kirchhoff's second law, we have E1 minus E2, which is equal to I2R2 minus I1R1. These laws are best understood through more numerical examples. So let's look at further situations.